beyond the last frontier any eye has ever reached, beyond the point where Neptune drifts in its frozen twilight, 4.5 billion kilometers from the Sun. There lies a region that for decades was described as empty space. That description stands as one of the greatest inaccuracies in the history of modern astronomy. What telescopes revealed out there is not nothingness. It is a vast zone of primordial material, stretching across tens of billions of kilometers, dense with frozen objects that have existed since before the Earth itself was formed, preserving secrets about the birth of the solar system in ways no laboratory on Earth could ever replicate. The Kuiper Belt is not the edge of our solar system. It is the place where time stopped 4.6 billion years ago, and we have barely begun to grasp the true weight of that statement. To understand what makes this region so extraordinary, we must start with scale. The scale of the Kuiper Belt is the kind of number the human mind genuinely refuses to feel in its bones, even when reason accepts it without difficulty. It begins where Neptune ends, at roughly 30 astronomicals from the Sun. 1 AU-Nuk, or astronomical unit, is the distance from the Earth to the Sun, approximately 150 million kilometers. The belt extends to roughly 50 astronomicas, meaning that sunlight, traveling at 300,000 kilometers per second, takes between 4 and 7 hours just to reach it. Think about that. The same light that touches your face in a fraction of a second needs nearly a full day of travel to illuminate the outer edges of the Kuiper Belt. And when that light finally arrives, it is so faint that the frozen objects dwelling there exist in a darkness no night on Earth could ever truly replicate. The Kuiper Belt is roughly 20 times wider than the asteroid belt, that ancient rocky band orbiting between Mars and Jupiter, which itself already spans hundreds of millions of kilometers. We are talking about a colossal ring of material that completely encircles the solar system, thick, ancient, and filled with objects ranging in size from microscopic dust to worlds hundreds of kilometers across. More than 100,000 objects, larger than 100 kilometers in diameter, inhabit this region. And that is without counting the trillions of smaller bodies, frozen fragments from an age before human history even began, drifting in absolute silence at temperatures of roughly -220 degrees Celsius. A temperature so extreme that nitrogen, the primary component of the very air you are breathing at this moment, it exists there not as gas, but as solid ice on surfaces that have never once been warmed since the universe first brought them into being. What lies there is not emptiness. It is an archive, a fossilized record of the chaos that reigned when the Sun was young and the planets had yet to find their permanent places. Every frozen object in the Kuiper Belt is a time capsule, preserving the chemical composition and physical structure of material left over from the protoplanetary disk, that immense swirling cloud of gas and dust that surrounded the Sun during its first millions of years of existence. In the regions closer to the Sun, that material melted, collided, and transformed into the planets we know today. But beyond where Neptune would eventually settle, there was never enough energy to complete that same process. The Sun, at that distance, simply does not radiate enough heat to reorganize matter into larger structures, and so these fragments remain, virtually unchanged across billions of years, frozen and silent witnesses to the very beginning of everything. What astonishes the researchers who study this region is not only what exists there, but what these objects reveal about the turbulent history of the primordial solar system. Computational models developed over recent decades suggest that the original Kuiper Belt was far denser and more populated than it is today. The most widely accepted theory holds that the orbits of the four gas giants, Jupiter, Saturn, Uranus, and Neptune, passed through a period of gravitational instability that profoundly reshaped the solar system during its first few 100 million years. In that reshaping, much of the belt's material was hurled into even more distant regions or flung violently inward through the solar system, triggering an era of intense bombardment whose scars remain visible on the surface of the Moon to this day. What we see today may be the remnant of a far more massive belt, and what survived carries the memory of that chaos locked within its orbital structure. A memory that science is only now beginning to truly decipher. Of all the worlds that inhabit the Kuiper Belt, none has captured the human imagination so completely as Pluto. For Pluto is 76 years from its discovery in 1930 to its reclassification in 2006. Pluto was considered the ninth planet of the solar system, a title stripped away not by diminishment but by revelation. As telescopes began to expose the true extent of the Kuiper Belt, it became clear that Pluto was no solitary anomaly, but the most celebrated member of a vast and populous family of similar worlds. Eris, Makemake, Haumea, Quaoar, names most people have never heard. Yet they represent real worlds with complex surfaces, unique chemical compositions, and in some cases, even moons of their own, orbiting in silence billions of kilometers from Earth. Pluto's reclassification did not diminish it. It revealed that the solar system was far richer and more complex than science had ever imagined. Pluto itself is a world that defies expectations in ways scientists are still working to fully understand. With a diameter of approximately 2,377 kilometers, roughly two-thirds that of the Moon, it harbors water ice mountains rising more than 3,000 meters high and vast plains of frozen nitrogen that flow with agonizing slowness, like glaciers moving in extreme slow motion. And a tenuous atmosphere that expands as Pluto draws closer to the Sun, then literally freezes and falls as snow when it retreats back into the dark. Pluto's surface displays patterns of light and shadow with a complexity utterly unexpected for a world so remote, including a vast, heart-shaped plain composed primarily of frozen nitrogen. Spanning an area roughly the size of Texas and Oklahoma combined, it stands as one of the most recognizable geological formations in the outer solar system. The New Horizons probe, which swept past Pluto in July 2015 after a journey of nearly 10 years covering some 5 billion kilometers, did not stop there. In January 2019, it reached an even more distant object, Arrokoth, previously known only by its technical designation 2014 MU69. Its shape resembles two lobes pressed gently together, the result of two bodies that merged in an ancient, almost imperceptibly slow collision billions of years ago. Arrokoth became the most distant object ever visited by a human-made spacecraft, positioned approximately 6.6 billion kilometers from the Sun at the moment of the flyby. What New Horizons found there was genuinely astonishing. A reddish surface, remarkably smooth, blanketed in complex organic molecules called tholins, compounds formed when ultraviolet light or cosmic radiation interacts with icy mixtures of simple gases like methane and nitrogen. Arrokoth revealed what the earliest building blocks of the solar system looked like and how binary objects like it were formed, not through violent collisions, but through a gradual, delicate process of gravitational orbital approach. The Kuiper Belt also harbors a phenomenon that connects this remote region directly to the visible sky above Earth, short-period comets. When a gravitational disturbance nudges an icy body onto an orbit that draws it progressively closer to the Sun, the result is a comet. Short-period comets, those that complete their orbits in under 200 years, and therefore return to Earth's skies at intervals humans can witness across generations, lives, are now widely recognized as originating in the Kuiper Belt. As the Sun begins to warm these frozen structures, the ice sublimates directly into space, creating the luminous coma and the distinctive tail that human beings have observed and interpreted for millennia. This means that every time a comet streaks across the night sky and stirs a sense of wonder, what you are witnessing is a fragment of the Kuiper Belt that has traveled billions of kilometers to appear on your horizon, the remote past of the solar system, literally paying a visit to the present. The diversity of objects within the Kuiper Belt extends far beyond its most famous examples. The bodies of this region are classified into families based on their orbital characteristics. The classical objects, which follow relatively circular orbits between 42 and 48 astronomicals. The resonant objects, which maintain a precise mathematical relationship with Neptune's orbit, make Pluto, which completes exactly 2 orbits for every 3 completed by the blue giant. And the scattered disk objects, locked in far more eccentric trajectories that stretch hundreds of AU from the Sun. Each orbital family tells a different story about how this material was distributed and reorganized during the first billion years of the solar system. The Kuiper Belt is not a uniform mass. It is a layered archive where the orbit of every single object is itself a historical document, waiting patiently to be read by those with the instruments and the perseverance to do so. There is a question that has kept scientists working with remarkable persistence. Is there a 9th planet hidden in the outer reaches of the solar system? Not the reclassified Pluto, but a genuinely massive world, one possibly carrying 5 to 10 times the mass of Earth, orbiting along a path so remote that a single journey around the Sun could take between 10,000 and 20,000 years. This hypothesis emerged from the observation of a deeply unsettling pattern in the orbital data. Several scattered disk objects, the most distant members of the Kuiper Belt family, have their orbits clustered in a specific orientation that seems far too precise to have occurred by chance. The statistical probability of this pattern being purely random is low enough that the idea of an as-yet undetected planet, informally called Planet 9, continues to be investigated with scientific rigor, even though no telescope currently in operation has offered direct confirmation. The logic behind this hypothesis is elegant in its structure. If a massive planet existed in a highly eccentric and distant orbit, its gravitational influence, accumulated over billions of years, would gradually organize the orbits of smaller surrounding bodies into specific, mathematically predictable patterns, exactly the kind of pattern observed in the available data. It would be like discovering that every compass in an entire city points slightly toward the same deviation from true north, and concluding that something must exist there, exerting an influence that instruments have yet to directly detect. The sky is vast, and the search for this hypothetical world is one of the most active frontiers in astronomy today. Specialized telescopes across the globe are systematically sweeping the outermost regions of the solar system, hunting for a point of light that moves consistently against the static backdrop of stars, Zeteran, the unmistakable signature of an object in orbit around the Sun. But even without a 9th planet, the Kuiper Belt has already revealed something profound and enduring about our place in the cosmos. For decades, the standard model of the solar system assumed that the regions beyond Neptune were essentially empty, extinct, a cosmic desert marking the boundary of solar territory inhabited by any significant bodies. What the astronomy of the last 3 decades has revealed is that this picture was fundamentally wrong. The solar system does not end at Neptune. It does not end even at the Kuiper Belt. Beyond it lies the scattered disk, stretching hundreds of astronomical units from the Sun, and beyond that, the Oort cloud, a spherical shell of frozen material that may extend as far as roughly 100,000 astronomical units, approaching nearly half the distance to the nearest star. The true boundary of the solar system lies far beyond what any current telescope can fully map, and the Kuiper Belt sits not at the end of that vast expanse, but relatively close to the beginning of it. Other stellar systems observed by modern astronomy also display structures analogous to the Kuiper Belt, known as debris disks, rings of icy and rocky material that persist around stars long after their major planets have formed. The Fomalhaut system, 25 light-years from Earth, hosts a sharply defined ring of material with structures that suggest the presence of planets within it. The Epsilon Eridani system, just 10.5 light-years away, harbors a debris disk with characteristics observed at radio and infrared wavelengths that closely resemble those of the Kuiper Belt. What this tells us is that our belt is no local curiosity. It is the solar version of a feature found widely across planetary systems throughout the universe, a legacy of the formation process that stars like our Sun appear to share on a galactic scale. To study the Kuiper Belt is, in part, to study how other systems around other stars assembled themselves from nothing. Until 1992, the Kuiper Belt remained a purely theoretical hypothesis. Astronomers had speculated about its existence for decades based on orbital calculations, but the first confirmed object beyond Pluto in that region was not detected until August of that year, a body roughly 200 kilometers in diameter, moving in an orbit consistent with the predictions. Since then, more than 2,000 Kuiper Belt objects have been identified and catalogued, and that number grows with every new sky survey conducted by increasingly powerful telescopes. Modern astronomy is not merely discovering individual objects, it is redrawing the complete map of the solar system, replacing the blank space beyond Neptune. With a landscape teeming with frozen worlds, complex orbital patterns, and histories that reach back to the very birth of the Sun, the Kuiper Belt was always there. It simply waited for eyes sharp enough to finally see it, and minds ready enough to look. There is one particular moment that is difficult to ignore when contemplating the Kuiper Belt in its full vastness, the passage of the Voyager 1 probe through the space beyond Neptune. Launched in September 1977, it crossed the region we now call the Kuiper Belt before science had even confirmed that region existed. There were no instruments aboard designed to detect objects of that family. There simply was not enough knowledge to know what to look for. In February 1990, Voyager 1's camera was turned back toward the solar system in a maneuver that captured one of the most breathtaking images in the history of astronomy. In that photograph, Earth appears as a tiny point of light, a fraction of a pixel, suspended within solar rays diffracted by the optical instrument, more than 6 billion kilometers away. The Kuiper Belt lay somewhere between the camera and Earth in that image, invisible, immense, and silent, waiting to be discovered by eyes that did not yet possess the instruments needed to see it. That kind of perspective, the one the Kuiper Belt inevitably imposes on anyone who pauses to truly contemplate it, is rare and genuinely precious. The existence of 100,000 frozen worlds beyond Neptune, each carrying its own formation history, its unique chemical composition, and an orbit shaped by gravitational events billions of years in the past, makes it impossible to keep thinking of the solar system as a small or fully understood place. The Kuiper Belt is physical proof that the Sun's neighborhood is far more vast than classical astronomy ever imagined, and that this neighborhood still holds surprises in store, from the possibility of a large yet undetected planet to the certainty that thousands of significant objects await names, calculated orbits, and detailed study by generations of astronomers who have not yet been born. The relationship between the Kuiper Belt and life on Earth is far more intimate than any distance might first suggest. The comets that travel from the belt into the inner solar system have delivered over billions of years, considerable quantities of organic molecules and water to the rocky planets. Growing evidence suggests that some of the water filling Earth's oceans arrived through comet impacts during the planet's first billion years, and at a period when the inner solar system was still receiving such material far more frequently than it does today. The very organic molecules detected on the surface of Arakoth, the reddish tholins, are precursors to amino acids, the building blocks of the proteins that make up all known life on Earth. The Kuiper Belt, therefore, is not merely an archive of the solar system's past. It may be part of the explanation for how life arose here. What lies frozen billions of kilometers away may have contributed to what exists inside your own body at this very moment. There is a question that this knowledge inevitably provokes. If the ingredients that made life possible on Earth arrived in part from the Kuiper Belt, and if other star systems possess analogous structures that deliver similar material to their own rocky planets, what does that imply about the possibility of life on other worlds? The answer that science is building, piece by piece, through the analysis of comets, meteors, and belt objects, is that the basic ingredients do not appear to be rare in the universe. Complex organic molecules appear in comets, in carbonaceous asteroids, in clouds of interstellar gas scattered across the galaxy. What may be rare is the precise combination of circumstances that allows complex life to emerge. But the fundamental ingredients appear to be a natural product of star and planet formation throughout the cosmos. The Kuiper Belt, in this context, is no local anomaly. It is a window into understanding how the universe organizes matter and possibly distributes the building blocks of life across the galaxies. What the reality of the Kuiper Belt ultimately reveals determines that we inhabit a solar system far larger, richer, and more dynamic than science long dared to imagine. Beyond Neptune, space is not empty. It is a frozen library, 4.6 billion years of history, preserved in ice and silence, inhabited by worlds that were never warmed enough to lose the memory of the sun's birth. Every object orbiting in silence through that region carries within it the story of the solar system's earliest moments, the conditions that made Earth habitable, and perhaps the very ingredients that made life possible. The Kuiper Belt reminds us that the frontier of the known has always been farther than we thought, and that every time science pushes that boundary, what it finds is not emptiness, but more universe than any previous generation could have imagined. It makes us wonder whether our own solar system still harbors entire worlds we have not yet fully mapped. What might be waiting in the systems surrounding the other hundreds of billions of stars in the Milky Way? Tell us in the comments what surprised you most about the Kuiper Belt, this place most people have never heard of, yet one that likely contributed in some way to your very existence. If this kind of deep dive into the cosmos speaks to you, subscribe to this channel and hit the bell. Every video is a new frontier waiting to be crossed. And if someone in your life needs to see the solar system through new eyes, share this video with them right now.